Welcome to the 2013 Sverdrup Public Lecture. This is part of our Sverdrup Visiting Scientist series. My name is Ben Stotrup. I'm an associate professor in the Department of Physics here at Augsburg College, and we're delighted to have all of you here this evening. So, this evening we are honored to have Dr. David Weitz, professor of physics and applied physics at Harvard University. And he will be presenting a lecture entitled Physics of Cooking. You may be aware, if you are a frequent user of YouTube, that Harvard has several lectures that are a part of their physics and cooking course online, where these lectures combine a world-renowned chef with an introduction to the science by Professor Weitz. If you have seen those, and hopefully some of my students in the audience have, you know that prior to the lecture there are several thank yous before the proceedings begin. So this evening we'd like to thank the Sverdrup family, and I believe Jean and her son George Sverdrup are both here tonight. The Sverdrup Lecture Series is in honor of General Leif Sverdrup, and was established in 1990. This series is also sponsored by the Minnesota NASA Space Grant Consortium, and we thank them for their generosity as well. We appreciate the help of General Mills and the Seward Co-op to get the word out about this exciting public lecture series, and so thank you. And finally, we appreciate, in our own course on science and cooking here at Augsburg College, the help of Landon Schoenfeld of Hot Dish. He came and gave a talk last week, and so please consider enjoying some fine cuisine, Midwestern style, downtown. Okay, without further ado, I think I will turn it over to Professor Weitz, because I think we've covered everything. Give or take.
Okay, so thank you, Ben. So I want to tell you a number of things. I want to tell you some experience that we've had trying to bring science, which is what I normally teach to the public. In particular, I want to tell you an experience I've had trying to teach people who don't want to study physics. How many here study physics? Whoa, poor you. How many here don't? Now, those of you who don't, what do you think of physics? Boring? Miserable? Imagine teaching physics to people who think it's miserable at 8 o'clock in the morning. That's what the dean does when he doesn't like the students who have to take physics. Well, that's what I did for a long time. And they didn't like me, and they didn't like the course, and I couldn't do much to change it. But I want to tell you about something where we did really change things. I got to teach a kind of physics course that I've always dreamed about teaching, but my colleagues would never let me teach because it's not traditional physics. But it is the kind of physics that I think you need. It all came about by a recognition that if you go not into a physics lab, but into a restaurant, you see a lot of really different kinds of food. So these are just some examples of the food that you see at some of the really fancy restaurants. I am not a cook, let me admit that. I know very little. I'm not even a foodie. I know very little about cooking, very little about food. Obviously, I do like to eat, but probably more than I should. But I'm not a fancy chef, but I've learned a lot. And I saw foods like this. Many of them were created by this man. He's Ferran Adrià. For many years, he was acknowledged as one of the really top chefs in the world. He's still acknowledged as that, but his restaurant, which is shown here, you can barely see it. It's a beautiful location on the coast of Spain, near Barcelona. His restaurant for a number of years was acknowledged as really the best restaurant in the world. I will tell you something about going there. Unfortunately, you could only go there in the past because it's been closed. And he's starting a foundation now to share some of his recipes. And when you go there, you see all kinds of foods that look like this. Really very different than certainly Midwestern fare and most American kinds of food. But this kind of cooking, sometimes it's called molecular gastronomy, but I think that the chefs actually don't like you to call it that. Perhaps a better word is modernist cuisine. This kind of cooking has permeated across the world to this country as well. Here's the dessert tray that you have at Abuli. Jose Andres is a chef from Spain, but he's based in Washington, D.C., and he runs a number of restaurants in Washington, D.C. He's also a well-known PBS lecturer, an excellent chef. Here's some of his restaurants. He has a series of restaurants in Washington, D.C. He's opened some in a variety of places. He opened one in Beverly Hills, which immediately became one of the best restaurants in the area. Some people will say it's really the best restaurant. So one day, we had a postdoc at Harvard who I worked with, Auger Campos, who was from Catalan, where Barcelona is, and he said, please can we invite Ferran Adrià to come and visit us? And he explained to me why we should do this, and I said, well, look, he'll never come. Why would you ever come to Harvard? We don't pay honorarium. We're not a fancy restaurant. He'll never come. But Auger was insistent. He said, please, let's invite him. So here's a picture of Ferran. So I wrote a letter. I was running a center which we could invite people. I wrote a letter the way I would normally invite a scientist. Please come and visit us. We'd like you to give a talk to a bunch of scientists at Harvard. And I gave it to Auger, and he translated it in Catalan because Ferran doesn't speak English. And I said, well, that will be the end of it, and we don't have to worry. But 3 days later, we sent it off by email. 3 days later, we got an email back, he's coming. So that was great. Of course, in my ignorance, I didn't know quite what to do, so we said, well, let's have a public lecture, something like this. We'll have a public lecture. And I went around and I found the biggest room. I didn't really prepare. So a few days before he came, I said, I better find a room. I found the biggest room I could, which was this beautiful refurbished lecture hall, which had 215 seats, each of them a very nice seat. I knew that later on. I found out exactly how many seats it had, because he arrived, and unbeknownst to me, there was an article in the Boston Globe about his cooking the week before. We just put a few signs up, Ferran Adrià, cooking and science, conversation on creativity. See, December 9th, 2008, 6:30 p.m. I just happened to walk by the lecture hall about 3:30, and it was sort of full. At 4:30, I walked by again, and we had to call the police because the people were jamming in in the aisles, and there was a fire hazard. At 5:30, I had to find a second overflow room. We webcast the lecture live on the web, and people lined up just to sit and listen to it nearby, Ferran. So he is really a remarkable person. This is, as a poor physicist, I'd never seen anything like this. I'm not associated with rock stars or other kind of people like that. But he really did attract a lot of attention. And he gave a wonderful lecture. And we asked, what could we do? What could we do after the lecture? What could we do together? And I looked at some of the creations that he has, and I see the foams, and I see the gels, and the emulsions. I say, that's exactly what I study. That's the kind of science I study. That's the kind of science that I'd like to teach to people. I'd like you to understand something about the nature of those materials. Yet when I try to teach physics, nobody's interested in that. Nobody's ever interested in that. Maybe they'd be interested in that if we could combine it with cooking. So there was born a class. We had a lecture series. Ben mentioned a bit about it. We had a lecture series, and that caused me to learn a lot about cooking and to learn a lot about food, but also the audience to learn a lot about the science the science behind the food. And I want to try and share some of both of these with you tonight. I want to share something that I've learned about the food. I want to give you some demonstrations, but I want to do it from a scientist's point of view. I want to explain things to you so you'll understand something of the beauty of the science as well as the interest and the taste of the food. So Ferran brought a whole series of very famous chefs, and the lecture was the course was designed that on Tuesdays the chef would lecture, and the rest of the class on Tuesdays and Thursdays the scientists, the professors would lecture. So it was a science class. It was based on cooking, but it was really motivated by cooking, but still it's a real science class. And so I'm going to show you things, but I'm going to try and teach you some science as well. And my colleague, Michael Brenner, was sitting on a committee at the time that was looking for courses for general education. That's our buzzword at Harvard for teaching courses to non-majors, so teaching a physics course to non-scientists. And he suggested that we do this course as that. So this is a course that's meant to teach science, but to non-scientists. And of course, I've tried to do that all my life. I've tried to teach non-scientists physics, and the dean knows the students. The students hate it. They really hate me. And the dean knows that, so he puts it at 8 in the morning. They hate it even more. So that's what I'm used to. But now I'm teaching a course of the kind of science that I really know and love, teaching based on cooking and doing it in collaboration with chefs. So that was a different sort of experience. We had a whole team of teachers. Auger is here, Michael. Jose Andres helped us. We had a whole team of people who developed the class with us. And it got a lot of coverage in the press. This is an article in the New York Times at Harvard, The Kitchen as a Lab. And when we started the course, remember, this is a science course. This is a science course. And Harvard, there's a liberal arts college. There are a lot of people who don't want to take science. There's only 6,400 students at Harvard. This is what it looked like when we first started.
Let's try to, so again, so I repeat, there are some seats. I don't know, I'm not exactly sure what you're supposed to do in a situation like this, but I just point out that there are some seats a little bit further. If some of you could move up, more people will get in.
So Michael also had never experienced like this. 700 people, 700 out of 6,000, 700 turned up to take a science class. You don't find things like that at Harvard, people wanting to take science, 700 people. Well, of course, we turned this, it's a science class, we turned this into a lesson. We said, well, okay, let's understand the numbers here. And we did a little statistics, and we gave the students a review of statistics. So here's a warm-up. This is how to think about things. So this is the odds of getting into the class. We could only take 300 students. So the odds of getting into class is about 43%. 300, well, there's 697 people who signed up for the lottery. There were many more who actually came but didn't bother signing up. So we had a lottery. So your odds are 43%. Now, if you're trying to take a physics class at Harvard, that's pretty poor odds, really, because all physics classes, you can always take them. But if you think about it, what have the kids done? Well, they'd gotten into Harvard. Your odds at those days were about 10%. Now it's about 8% to get into Harvard. But if you want to see really bad odds, the restaurant of Ferran, the odds of getting into that were about 0.5%. So that's a very, very difficult, it was a very difficult restaurant. Just by way of explanation for those of you who may not have heard of El Bulli, he opened it only 6 months a year, only for dinner. The other 6 months, he worked in a little lab in Barcelona to create new dishes. So it was only open for 6 months, only for dinner, and in order to go to the restaurant, you had to sign up. 1 day a year, you signed up on the web. Near the end, if you signed up on the web, if they were to try and give everybody who signed up on the web a seat, it would have taken 125 years. So it's a very popular restaurant. It doesn't exist anymore, so you can't even dream about trying it. Well, okay, so it obviously created a lot of buzz. This is sort of why.
Because it's something different and it's something that's like common, like cooking and stuff like that. It's like something fun, but it's related to something that's usually possibly boring, like physics.
These are Harvard students explaining why they were interested in the class. There was the Harvard magazine did a little video thing. You can find this on YouTube, in fact. They did a little video presentation interviewing students as why they were interested in the class, because it really created a lot of buzz. None of that was planned. It was all it just happened. So the class had a lab. It was a science lab. It had a class that had to have a lab. We were very fortunate. We found a lab in a new building that had never been used, so we could declare it food safe. And we got the university to dedicate it to food as a food lab for 5 years. It was just by luck that we could do that. And so you go into the lab and you see it's a normal lab. There's all kinds of things. There's cutting boards, shakers, funnels, thermocouples, all the sorts of things that you need in a kitchen, scientific instrumentation, and cooking instrumentation. And in addition to the lab, we have a recipe. You have to cook something every week. This is one of the key foods that we cook. This is molten chocolate cake. It's chocolate cake. It's molten in the middle. By measuring how long it takes to solidify, you can see the middle is soft. Measuring how long it takes to solidify, we're able to teach something about the diffusion equation, about the diffusion of heat, in a very simple way, and do experiments. And so we do experiments and we cook something. In fact, the lab was something that was of great interest to the students.
What are you looking forward to the most?
The labs, I think.
I think the fact that you can eat your lab is pretty much the coolest thing ever.
So in fact, you do eat your lab. This is the creation from one of the labs. This is some students who cooked something and then tried to put it on a plate to make it look good. So you both combine real science, which I'm going to show you here, with cooking things and eating good food. And we had a textbook. There actually wasn't a textbook that we could find, so we were very unfortunate that one of the teaching fellows who worked with us was John McGee, and his father, Harold McGee, wrote a book in the 1980s called On Food and Cooking, which is really a wonderful book that explains food from a very scientific perspective. It's one of the few books that actually do this. And so we adopted that as the textbook. Of course, there are other books that are around. Nathan Myhrvold, the former CTO of Microsoft, who now runs Intellectual Ventures and Modernist Cuisine, has written a book here. The problem with this book, we thought it probably wasn't quite suitable for a textbook for the class, because the cost of this book, when it had just come out, the cost of this book is $500. It's well worth it to buy the book, but it wasn't good for a textbook. And we actually got Harold to come and give some of the lectures. He's a wonderful lecturer, very knowledgeable. And it turns out that he knew a lot about Harvard because he wrote the book at Harvard.
I can't tell you how amazing it is to be standing here today. I'll try to explain, but it's going to be hard to explain. I wrote on food and cooking essentially in this building. And one of the ways it's changed is the fact that I'm standing here talking to all of you. I never in my wildest dreams thought that Harvard would ever teach a course in the science of cooking, to say nothing of my book, the book that I was writing then, being used as the textbook in that course. So this is completely mind-blowing.
So that's what he thought, and I think most of the students as well thought that it would be completely mind-blowing that you can take a course on cooking and science at Harvard. So it was a new course, and we got to establish new traditions. So every week, we really wanted to have a science course. So every week we had a lab, we had a recipe of the week, we also had an equation of the week. So every week you had to learn an equation. And here's Michael introducing the first equation of the week.
These must be equal. It must be the case where motion and sticking are in exact balance. That's our equation of the week. You're all supposed to clap.
So that's a new tradition. You have to clap whenever we see an equation. Let me repeat that. You have to clap whenever you see an equation. When you see an equation. In fact, we did get the class to do it. We also got the public to do it. So how often you had undergraduate non-science majors clap when you show them an equation? Ben, do you ever do that? It's very difficult to get them to be interested in equations, much less to clap. But you did hear what I said, right, when it comes to equations. So we had a lot of lectures, Ramon Ramada, Enrique Rivera. We did a lot with chocolate. Here's Enrique in the lab demonstrating some nice creations that he made of chocolate. Bill Yossis came. Do you know who Bill Yossis is? Maybe you'll recognize him here. He's the White House pastry chef. This is one of his creations. He's also a wonderful, wonderful teacher, very, very knowledgeable and very interested in sharing with the rest of the world what he does, sharing his kitchen. And he claims that the current residents of the White House are very much like that, Mrs. Obama also wants to share the kitchen with the rest of the country. This is what Bill made. This is olive oil gelée. He took olive oil and made a jelly out of it. And he served it to 300 students. This is a very, very interesting material, a very interesting dish. I would love to tell you more about it, but I won't have time. But it's a very unusual thing to create that. And the science of this is very interesting. So what really is cooking? So now I turn to somebody like myself. As I told you, I don't know much about cooking, but no, I can cook an egg. Sort of. So let's see. These are eggs. It's not cooked, right? It's liquid, right? What happens when you cook it? This is more or less solid, hard-boiled, but it's not quite. It's solid, right? Going from a cooked to an uncooked egg, we go from a liquid to a solid. Okay, well, I'm a physicist. I understand things like that. I understand what liquid is, and I understand what a solid is. Water, that's a real common sort of thing. Here's some water. Here's the solid form of water, right? Ice. That's solid. How do I make ice? Well, I cool it down. So materials undergo phase transitions. If you heat things, they go from a solid to a liquid to a gas. We know that about water. At 0 degrees centigrade, water freezes and turns from a liquid into a solid. At 100 degrees centigrade, the liquid boils and becomes a gas. That's a phase transition. We understand that. So if we want to cook things, if we want to change things from a liquid to a solid, we have to make it undergo a phase transition. And we just saw how we should do that, right? We should cool it down. So let's cook an egg. I think I know how to cook an egg, right? I have to cool it down. Of course, I'm a physicist. I want to do things in a... Did I just do that? I want to do things in a sort of brute force way. You might want to see this one. Camera. Everybody know what this is? See, when I want to cool something down, I don't fool around. I get something really cold. So this is obviously how you cook an egg, isn't it? Don't you think? Here's an egg. Let this calm down for a bit. It's boiling like that because it's cooling the water, they're cooling the glass, and it boils as it cools. It turns into nitrogen. Okay, well, let's cook the egg. Okay, we have to cook it for a few minutes. While it cooks, how long do you cook an egg for? 3 minutes? Okay, well, let's cook for a few minutes. While we're doing that, I'll go back and I'll tell you a little bit about the science of what we're doing. And we'll come back and we'll check our egg in a minute. So what we're doing is we're changing things from a liquid to a solid. On a molecular basis, if you look at the molecules inside the material, if it's a liquid, the molecules are still held together, but they can move around, and they can move over over each other, so they can flow. If you cool them down, you take energy away from them. If you cool them down, I don't know what that was. We'll find out. If you cool them down, they become a solid. And they're stuck in the same place. They still move, but they don't move so much that they can flow over each other. They hold their same position. Of course, if you heat them up until they evaporate, until they boil, then the molecules are a gas and they can go everywhere again. They can go all over the place. So remember, the simple way of understanding these different phases is a solid will sit here. It won't move. It won't go anywhere. A liquid will flow, and a gas will go and fill the whole room. And so that, of course, gives us some idea of what temperature is. Temperature is just the amount of energy that the molecules have. It's a measure of the energy, the temperature. The higher the temperature, the more energy they have, and the more they can move. That's a simple way of understanding it. So this clearly is the best way to cook an egg. Should we see if it's done? The explosion we heard was the egg exploding. Oh, sorry. Let me see. Camera. I'll share this with you. Can you zoom in a bit? Good. You see the way it's cracked? Do you think it's solid? For this, I'll use my glove. There. That's solid, right? I've obviously cooked the egg. So that's clearly how you cook an egg. I'll put it back on. Oh, it's not, you told me it was 3 minutes, right? It's slightly soft. It's not completely hard. Can you show that right here? Can you see this? You zoom in, you see? There's still a little liquid there. The difference between this cooked egg and the egg that you normally cook, and here's some cooked eggs, which I'll open in a second. The difference between that is that this one will eventually melt and become a liquid again. This is a cooked egg. This looks perfectly cooked. Perfectly cooked. And what's happened here? Let's go back to the slides for a minute. We'll go back to the camera in a second. So what's happened here, how we normally cook an egg, is that we take advantage of the structure of an egg. It's made up of proteins. Proteins are these long molecules that are balled up. They're nicely folded. If you heat them up, you denature them. You cause them to unfold. And they move around and they spread around everywhere, and they become very sticky. So they stick to each other. And rather than being in a little ball so it's a fluid, they spread out and they form a solid. And it's by denaturing things that you can actually do that. And so you form a solid. But you said, when I asked, how do you cook an egg? You said 3 minutes. You cook at 3 minutes. Why 3 minutes? What temperature do you normally cook an egg at? How do you cook an egg? You boil it. What temperature do you boil the water at? 100 degrees, right? So you cook an egg at 100 degrees for 3 minutes and you get a soft egg, right? At 10 minutes you get a hard egg. Time takes it. But really what's happening is that it's a temperature. It depends on the temperature. And eggs cook at a very, very precise temperature. And we did an experiment. I don't know if it'll work. Experiments, you never know if they work. We cooked eggs at different temperatures. And we're going to open them up and have a look at them. So Ben was really kind to help us. Which is the 59? This egg was cooked at 59 degrees. I'll take them out and I'll open them in a minute. This one was cooked at 63 degrees, just a few degrees different. Do we know the temperature of this? This was cooked about 66 or 67. Again, just a few degrees different. So let's have a look at them. That's not really quite cooked, right? 59. 63. There's an almost perfect soft egg. Right? It just flows perfectly. 66. This is already more cooked. The yolk is already hard. So you see how closely temperature, how well you can control temperature. So the fact that you cook it for a certain amount of time is only because you want to get a certain temperature. These eggs were cooking for about a half hour at these temperatures. You can cook them for all day and they'll stay perfectly cooked. 63, 64 degrees, that's the temperature you cook an egg. That's the temperature you get the perfect soft poached egg. You change it just a couple of degrees either way. A couple of degrees lower, it doesn't cook. A couple of degrees higher, it cooks too much. So the time is only because you want the egg to warm up a certain amount, because you're cooking it at a much too high a temperature for the actual temperature that you want to cook the egg at. And that's because the egg is made up of proteins, and proteins are denaturing, and as they denature, they unfold, they spread, and they form a network. And that occurs at a very precise temperature. They're proteins that occurs at exactly this temperature. So 63 degrees is the temperature to cook an egg. So what other things can we do to change to control the behavior, the phase behavior of food? Well, I showed you can control temperature. Another thing that physicists that we like to do, is control the pressure. When we think of phase behavior, we often think about temperature and pressure. And so we can also change the pressure. And you know, actually, if you ever have been into the mountains at high elevations, you know that pressure plays a big role when you cook. Has anybody here ever gone to high elevations? Has anybody climbed? How high have you climbed? 1,400? 1,400 feet's not very high. Anybody go a little higher, like 14,000 feet? 14,000, yes. 12,000. Did you ever cook at 12,000 feet? Has anybody cooked at high elevations? Yes. What happens? Takes forever. Why is that? Well, what we do is we try and transfer heat from boiling something. And so if you boil water, it boils at 100 degrees C and it cooks at 100 degrees C. You see, for eggs, you want to get the egg to about 63 degrees C, but it takes time. And the hotter it is on the outside, the less time it takes. Well, if you look at the behavior of the boiling point of water as a function of pressure, you see that as the pressure decreases, so when you're at 3/4 of an atmosphere, that's not that high. That's maybe 10,000 feet. If you're at 3/4 of an atmosphere, the boiling point is really only 92 degrees. If you go much higher, it rapidly drops. And that's why it takes so long to cook, because you're using much lower temperature water. Has anybody tried to cook pasta at high elevation? You can't. You can't cook it at high elevation because it doesn't get hot enough. You can't get al dente pasta at high elevation. So you can think of this more generally. You can draw a two-dimensional phase diagram, and this is the two-dimensional phase diagram of water. This is the pressure, this is the temperature, this is the boiling point. And you see that at atmospheres here, you go to lower pressures, that's higher elevations, the boiling point goes down. If you increase the pressure, the boiling point actually goes up. The solid to liquid line doesn't change very much with pressure, and that's because everything is already condensed. The reason it changes is that the gas is at low pressures, and if you change the pressure of the gas, you change how it evaporates, how it boils. So now if you sit at room temperature and you try to heat something up, if you're at low elevations, you heat it up, it goes to a much lower temperature. But just looking at this phase diagram, you can immediately understand how a very common cooking tool works, and that's the pressure cooker. Who here uses a pressure cooker? So a pressure cooker, what do? You put this little bulb on top and you increase the pressure. And so if you increase the pressure on the inside, this is what happens. The boiling temperature goes up. So you boil water at a higher temperature, and that's why things cook faster, because you're literally just increasing the pressure and therefore increasing the boiling temperature of water, increasing the heat that the water can give to the food. The pressure cooker, when it was first invented, was invented in England, and it was used primarily to cook things like meat and bones, because it would make bones into basically mush that you could eat. And that was something that was of great interest to the chefs in those days, or the cooks in those days. Of course, you can also lower the pressure rather significantly, and then things boil at a much lower temperature. And so if you want to distill something, if you lower the pressure, you can distill it at a much lower temperature. And that's a rotovap. This is a common instrument in chemistry labs, but it's now used in kitchens as well. And so you can distill things and extract the flavors at much lower temperatures by decreasing the pressure. And here's an example. This is another example of one of the chefs showing something in our class. He called it a really super cool dessert. And so what did he do? I'll show you the movies. This is a video of a chef who spoke only in Spanish, so there's a translation. I will also translate a bit and tell you what he's doing. He's making a dessert.
Fem un destil·lat d'eucaliptus.
This is distilled eucalyptus.
So he takes eucalyptus and puts it in water, and then he puts it on the rotovap.
Amb el rotaval
We use the rotaval.
And he extracts
aconseguim
the
captar l'aroma volàtil de
aromas
So
and
we
the
capture
flavors
the-
from the eucalyptus.
Amb l'eucaliptus
We
And so he's
distill the
extracting it. This
eucalyptus.
is the water, the
i
purified
aquest
water.
destil·lat d'eucaliptus el posem en un congelador a
He
5
puts it in a refrigerator.
graus sota zero. 5,5 graus sota
And
zero.
look at the
We
temperature of the
place that
refrigerator.
in a freezer.
-5 degrees. So he puts the water, this distilled water, in a refrigerator at -5 degrees. What's the freezing point of water? -5 degrees.
La flor del gel
He
que
makes a
hem fet
nice
abans,
dessert.
Snowflake,
aquest meló gelat.
the frozen melon.
This is the
I
water.
aquesta és l'aigua, que està líquida encara,
And this is the water still,
still liquid.
in liquid state.
però quan cau a sobre el meló congelat es congela.
And he pours it.
Això ho fem a la taula, fa el cambrer a la taula.
That's the clapping of the class. And so that was, we immediately had a new tradition. You clap when you see a great dessert. Now why? The chef called it super cool. So we thought, oh, it'd be a really cool dessert. Super cool, it's really cool. But what he meant was it's super cooled. So you can cool water below 0 degrees C and have it remain a liquid. In fact, you can cool it down by 20 or 30 degrees C and have it remain a liquid if there's no way for ice crystals to form. If you prevent the formation of ice, it remains a liquid. And that's what he did. And then as soon as he poured it, the shaking caused it to solidify, and so it solidified as it came up. So he meant it was a super cooled dessert, not a super cool dessert. But it was indeed a super cool dessert. So let's tell you some more things that we do in the class that we teach about. One thing is elasticity. You know elasticity because things are elastic, they taste differently. If you cook a steak, the more you cook the steak, the tougher it is, the more elastic it is. The elasticity increases, the elastic constant increases. And so the mouthfeel, how things taste, is very strongly affected by the elasticity. So an egg, when it's more or less soft-boiled like this, tastes and feels differently in your mouth than a hard-boiled egg or an egg that's just barely cooked. So how do we actually quantify it? Well, to understand something of elasticity, I'll go back to something, a very simple way of describing things. I'll start with a spring. So if you take any physics, you will have studied what a spring is. You know what a spring, it looks like this. But if I take a spring, I just hang it like this, there's some natural length to the spring. And if I take a weight and hang it on the end of the spring gets longer. The weight pulls it down. And I know the weight here, and I know the length, and now it's stopped, and this extra length of the spring I can calculate the force due to the spring. It's increased the length by this delta L, by this change in length, and the force is just equal to the force of the weight. And so the force depends on how much you lengthen it, and so if I measure how much you lengthen it, I can measure what's called the spring constant. The spring constant is a parameter that tells me how stiff the spring is, how elastic the spring is. The larger this number is, the more elastic the spring is, and the less it will stretch for a given weight. Well, we can do the same thing for food, and we can understand the behavior of food. Clap. In this case, for food, we don't want to worry just about the force. So we take the force. We don't want to worry how big the food is, so we divide it by the area of the food. So the force divided by an area is what we call a stress, a force divided by an area. And since we don't want to know, we don't care how big the food is, we measure the relative change in length, or we measure the relative displacement, so we normalize the change in length by the initial length. And so there, we have a way of measuring the elastic constant. It's the force divided by the area, and it's the relative change in length. And we can do this. We can make this kind of measurement. You've clapped already. We can make this kind of measurement. We can use our favorite ingredient, the egg. So let's see, I have a hard-boiled egg here. So I could use this, and I could peel it. And then I could, once I have it peeled, I'm not going to do that because it'll take too long, I can take a knife Where did my knife go? I can take a knife and I can cut it so it looks like this with nice flat faces. And then I can just measure how much it's displaced if I put a weight on it. So here's a weight. I can measure how much weight it is. Let's see if I measure this. This is 300 grams. Measure this. And here is an egg. And I can measure its height. I've actually measured this before, so I know it. Its height is 3 centimeters. And now I'll put this weight on top of it. And I have a ruler behind. And I can measure the displacement. That's okay. It was displaced about 3 millimeters. Do it again. Its displacement is about 3 millimeters. I've actually done this before, so I know it. And I can measure the area of the egg. So I'll take it roughly as a sphere. It's about 6 centimeters in diameter. So about 3 centimeters in radius. So let's go back to my slides. So what I did was I put a weight on the egg. I know the weight is 300 grams. I measure the displacement. And so what do we need to know? We need to know the force applied to the egg, the area of the egg, and the amount of deformation. We use our equation. So this is the numbers I told you. It's 300 grams or 0.3 kilograms. The radius of the egg, half the diameter, is about 3 centimeters. The height is also about 3 centimeters. And the deformation was 3 millimeters or 0.3 centimeters. So now I can just use this equation. Well, first I have to calculate the force. The force is the mass times the acceleration of gravity. I'll take that as 10 meters per second squared. So the total force is about 3 newtons. And the area is pi r squared, so I just take pi times the radius squared, and I've converted this into meters, and I get about 10 to the minus 3 square meters. 2 times 10 to the minus 3 square meters. And the displacement is 0.3 divided by 3, that's about 0.1. And so from this I can calculate the elastic constant. It has units of pressure. A force divided by an area, this has no units, so this has units of pressure, and it's 1.6 times 10 to the 4, or 16 kilopascals. And I know from experience that that's about the right order of magnitude for the elasticity of something that you can easily chew. So for example, in our class, we cook a steak, and we measure the elasticity, the elastic constant of a steak. If it's rare, the elastic constant is about 45 kilopascals. That's basically consistent with what you might think. The egg is much softer, particularly this is not really a hard-boiled egg. It's softer than a steak, and its elastic constant is less. It's about a third of a steak. It's 16 kilopascals. The steak is 45 kilopascals. If you cook the steak more, it goes up to 65 kilopascals. It gets tougher. You know that when you chew it. If you chew a well-done steak, it's tougher than a rare steak. And if you measure it, you find exactly the same behavior. So that's a way that we can quantify the mouthfeel, the elasticity of some food. Now there's another very interesting solid, that's a gel. A gel is primarily water. It's small amounts of long molecules called polymers in water. Here's an example of a gel. This is taken from Nathan Myhrvold's website. This is a very high-speed camera image of a gel bouncing on the surface. And so you can see it sort of looks like water, but it's also a solid. It looks like it's spreading like water, but then it recovers and becomes a solid. I think there's another one that's going to come in a second. Yeah, here comes another one. You see the way it spreads like water, but then stops because it becomes a solid. So a gel is made up of these long molecules, these polymer molecules. They're very flexible. Alginate's a very common one. But when they spread through the fluid, they behave like a solid. Why is that? We can understand the elasticity of a gel in a very, very different way. It is elastic, but its elasticity is very different than anything else that we're used to. Its elasticity comes because the molecules are very flexible. They don't like to be stretched. In fact, if you stretch the molecule, there's only one way that they can exist, as a straight line. But if you allow them to be less stretched, there's many more ways that they can exist. And in fact, if you allow them to be even less stretched, there's many, many ways they can exist. And in fact, the molecules like to have lots of different ways that they can exist. And if you stretch them, you reduce the number of ways that they can exist. And reducing the number of ways actually costs energy. And if you store energy, it's elastic. And that's what causes the elasticity. So now you can understand the nature of a gel. It's all these flexible molecules in the fluid. It's mainly water. They're a very, very small amount of material. It's mainly water. And if they're stuck together, so here there are certain points where they cross, they're stuck together, they can't escape. And this network becomes a solid, but it becomes a solid for a different reason. There's a characteristic length scale. It becomes a solid because if you stretch it, you're changing the configurations. So here we're stretching it, we're changing the number of configurations. That becomes a solid only because of the difference in configurations. And so that gives it a different kind of elasticity. Now the elasticity depends on thermal energy. It depends on the fact that thermal energy allows the molecules to sample all these configurations. And if you change the configurations, you change the elasticity. And it depends on the length scale. If I go back here, this length scale, that tells me how often I have a bond. That tells me the density I have a bond. So this is the formula for the elasticity. And there's a very common type of gel that's used often in food, that's alginate. Alginate is made from seaweed, and it can be cross-linked very easily. And this leads to a type of a dish that Ferran was created in the original, and Elena here will help us and try and demonstrate this. She learned how to do this last week in Ben's class, and this is called spherification. And so what we have is a juice. It's slightly thickened. This is pomegranate juice. It's been slightly thickened with alginate. And this is some calcium in some water. And what Elaine is going to do is take a small sphere of this and put it into the calcium and then wash it off. Do you want to try that, Elena? If you want to use this, or you can use a spoon. It's actually up to you. We'll use both. You want to use the other spoon? Lots of paper towels here. Better wash it off. Wipe it off. See this. You want to do some of those? Needs a little bit more time. Go ahead. So I'll just rinse this off a bit. I think I broke it. I shook it too much and I broke it. Let's see if I have another one here. Yes. So you see how spherical, it doesn't really show too well. Let's see if I can. Oh, that's good. See how spherical it is? I'll try and reflect the light into it. If I cut it open, it's still liquid on the inside. So what this is, it's alginate on the inside. We've added a little alginate to the juice. And then there's calcium on the outside. The calcium causes the alginate to gel, and it just gels on the outside. It forms a shell of alginate, of solid alginate, around the outside. And the inside is still liquid. So if you bite into it, you still get the taste of fluid. There's just a small shell of that. So this is what happens. It's alginate on the inside. We put in a bath of calcium. The calcium causes the alginate to gel, to form a solid. It forms permanent bonds. But as you allow it to sit, the calcium moves in, and more of the solid, and more of the liquid becomes a gel. In fact, if you waited a long time, the whole thing would become a gel. And so if you're actually trying to serve this in a restaurant, even if you take it out and wash it the way we did, you can't prevent the calcium, whatever that calcium is left, from diffusing in, and eventually it becomes a solid. So this is called direct spherification. This is the first thing people did. But then they realized that you could do something different. You could take a material that has calcium on the inside and put in a bath that has alginate. And then alginate would coat the outside, and then if you take it out, it can no longer form a gel because there's no more alginate. And so we have another example of that. This is called inverse spherification. Elena, do you want to try this? This is made with yogurt, which has a lot of natural calcium. Here, I'll get 2 more towels. Yeah. Write it on the bottom first. Down here. Write it. Yeah. Perfect. So we'll let these solidify for a minute. Do you want to wash that spoon out? These will be a little easier to see because the color is right. Where's my water bath? You stole my water. Oh, there. I'll wash the remaining alginate off. And now we have a perfect sphere of yogurt. And this won't age. This can be kept. And if you cut it open, it might knock off. It's still yogurt on the inside. It's still fluid-like on the inside. So this is a way of creating food that has a solid shell but remains fluid, or whatever the consistency you started with on the inside. And maybe after it can make a few more if people want to try it. Okay, let's do a couple more things. I'll skip through this. So another thing is an emulsion. An emulsion is a very interesting material. It's just fluids that are mixed up and made into a solid. And you're familiar with this if you think of something like mayonnaise. And I'm going to make something quickly with mayonnaise. Actually, maybe I'll, given the time. Do people have to go very soon? Because if you do, I'm going to stop in a couple of minutes. You want to keep going? All right. So we'll have fun. So if you want to leave, just go ahead. There's about 5 or 10 minutes more. I have to just prepare some things for what we're finishing with. A couple more demonstrations. Got to prepare the last one. That's an important one. Making mayonnaise. So, does anybody know what mayonnaise is? Oil? Egg yolks? So, we need an egg yolk. Do you trust me? See if I can do it. Here's an egg yolk. That's pretty good. So egg yolk. We need an egg yolk. You need a tablespoon of water. These are both liquids, right? Need something to make it taste good. Mustard. It says a dollop of mustard. Does anybody know what that is? That's a dollop of mustard. And the juice from a lemon, half a lemon. So Elena didn't want me to do this. She's afraid that blood is going to come into the mayonnaise. I assured her that I'd try very hard to. Okay? You didn't have to worry after all, Elena. Lemon juice. Be a few seeds, but that's okay. And then a cup of oil. So here's oil in a cup. I think that says a cup. And so I'm going to pour this gently in. And the oil all stays on the top. But now I'm going to try and mix it. And let me warn you that I always get this wrong, so it doesn't always work when I do it. My students can do a really good job. But I'll mix it just from the bottom. So all I'm doing is mixing fluids together. Now if I take some of this, I've just taken fluids, right? All I've done is take fluids, and you can see it's a solid. So just by mixing fluids together, you end up with a solid. I won't do this, but if we had more time, I'd add just a little bit more oil, add a little bit more fluid, and it will become stiffer, become more solid-like. So let's go back and understand quickly what we're doing. We're making an emulsion, so we're making drops of one fluid in another fluid. In this case, it's drops of oil. Mainly, it was 1 cup of oil. It was probably a quarter of a cup of all the other fluids. We're making drops of one fluid in the other fluid. And in order to make them, we have to somehow keep them stable, and that's what we use the egg yolk for. The egg yolk forms a wonderful surfactant. A surfactant is a surface active molecule. It's a molecule that's slightly oil-like and slightly water-like, so it lives on the interface between the two fluids. An egg yolk is the best surfactant there is. And so when two bubbles come together, they can't stick. They can't coalesce because the surfactant keeps them stable. And then it's solid. It becomes solid-like because you're trying to squeeze the bubbles, make more and more bubbles, and you're trying to squeeze them into one place. And the bubbles can't stay as the spheres that they'd like to be, the drops of the oil. You have to deform the drops of the oil. And if it takes a force to deform a drop of oil, you know that if you take a balloon and you try and squeeze a balloon, it takes a force. It's the same thing. And the fact that you're squeezing these things is what makes it into a solid. The fact that you squeeze them together. The drops want to spread apart, but they can't because they're held in by this continuous water phase. And they're stable because of the emulsion. So a mayonnaise, an emulsion, is an amazing kind of solid. It takes two liquids and you mix them together, and just by mixing the fluids together, you end up with a solid. And in fact, the elasticity, the elastic constant, depends on how much of the internal phase, how many drops there are. If you have only a few drops, that's like milk. It flows like water. You have to reach some critical point, some value of the volume, some amount, some density of the internal phase before you deform them and become solid. And then the elasticity increases as you increase the solid. And we can parameterize this. I won't go through the details, but I will show you the equation. So the equation tells you, depends on the volume fraction, how far you are from this critical point, from where it starts. And if you make the drops smaller and smaller, the elasticity gets larger and larger. A foam is exactly like an emulsion, but you replace the internal phase with rather than a fluid, you replace it with air. And we have an example. Whipping cream. Who likes whipped cream? Who makes whipped cream at home? I need somebody who really likes to make whipped cream. Come on, good. She's looking at this and she thinks she's going to use this. I cooled the bowl for you. Put in the ice. She's an expert. She says it needs to be cold. But we have ice here. Okay. Let's make some whipped cream. A little vanilla. That's a little more than you normally get, but okay. Okay, you're on. While she does that, I'm going to show you another way of making whipped cream. Keep working. Sorry, I'm lazy. Here's some whipped cream. How's it coming? Oh, you're doing well. A little vanilla. Oh, good. It's doing well. A little canister of gas. That's doing pretty well. Who goes to Starbucks? Has whipped cream in Starbucks? You were a barista there, right? They could make it like that in Starbucks. But this is much easier. You ready? It's whipped cream. How are you doing? Oh, it's coming. It's doing well. Well, come on, you can do better than that. You said you were good at making whipped cream.
I need a tall bowl.
Oh, she says she needs a tall bowl. Come on. See if we can make some. Actually, there's a reason for doing this, that this whipped cream is really much tastier. And I'll explain, if we can make this into whipped cream, I'll explain to you why that is. So what are we doing? We're just basically putting air into the cream, and we're making bubbles, and the bubbles, when they get enough bubbles, they squeeze themselves together in the same way that the liquid drops do, and they become a solid. Okay, this is close. You finish. I want her to finish because I want to explain. Can we go back to this? Thank you. I want to explain what we're doing. In this case, what was your name, Joan? Janet. Janet was whipping away, getting very tired. I don't blame you. I was too. Now poor Elena's doing it. Here, what we did was we took these canisters of compressed gas and we, under pressure, mixed them together. We mixed them together. These are gas under pressure, and this canister is under pressure. We dissolved, the gas became a liquid. As high enough pressure it became a liquid. The gas dissolved as a liquid into the cream. It's liquid. It's liquid here because it's under pressure. Then when we lower the pressure, and this comes out, the gas expands and forms bubbles immediately. That's pretty good. The difference is that when we mix it, let me just take a look. When we mix it, here we've really made bubbles very stably. There's small particles of fat inside. They've gone to the edges of the bubble, to the surface of the bubble. And if we watch this, you'll actually see that this stays as a nice cream, as a foam, much longer than this. and it has very different consistency. And again, if you come up afterwards, you can taste it and see what it is. You'll see they taste very different. So this is a very quick way to make foam, but it doesn't taste as good and it doesn't last as long. Okay, just do it on the side. Thank you. Okay, let's finish with one thing. When we finish with something, you know, it's tough work. Time for a drink. I want to teach you a little bit about drinks. This is a martini. Who likes martinis? Shaken or stirred? Both. They do taste differently. Okay, so I'm going to make a martini, but I'm going to do a little experiment when I make them. What I'm going to do, the recipe for the martini basically calls for a mixture of gin and vermouth or martini mixed together on ice. These are both at room temperature. This is ice. It's in water. I did that purposely. What's the temperature of the ice? 0 degrees, you say. Well, let's measure it. It's going down 0.4, 0.2, 0 degrees. Okay, so the ice is at 0 degrees. These are at room temperature. I'm going to make it now. I'm going to mix them together. My jigger. So let's see if I get the right ratio here. Four gins. I'm making 2. Four gins, and then I'll need, oops. One of these. There we go. What's the temperature of the alcohol? It's room temperature. 20 degrees, 24 degrees. I'm going to put the ice in here. I'm going to mix. I put it in this water bath to make sure that I'm starting with ice at 0 degrees C. And I, of course, like mine shaken, so I'm going to shake it. What's the temperature going to be when I finish shaking it? Anybody want to tell me? Pardon? 0 degrees C. After all, the ice is at 0 degrees C. If I were the right kind of bartender, I'm not. Okay. See if I can take this up. Let's measure it. Can you see that? No. Okay, Elena, you better read it because I'm not sure I believe it. What does it say, Elena?
Oh, -6.
Say that again?
-6.
Say that louder.
-6.
Do you get that? -6. -6 degrees. And if you feel it, you'll see it's cold. I've cooled the ice lower than the temperature it started with. Do you get that? Isn't that amazing? Why is that? It's because I take alcohol and water, and the melting temperature of alcohol and water is lower than that of water. It's lower. It lowers the temperature. So the ice is trying to come to some equilibrium. It's trying to come so that it's at the same temperature. It's cooling itself. It can cool itself below the temperature it starts with, because as it melts, as the ice melts, it takes heat to melt the ice. It cools all the surrounding because it takes that heat. to melt the ice. And you can cool the ice lower than it starts with. You're cooling the alcohol and water as well, but you're cooling the ice also. So you've actually cooled it to a lower temperature. So now I think we should have some. Of course, we should always ice the glasses before we start. And of course, when I ice glasses, I don't fool around. Let's ice these glasses up. And then we can have a drink. Isn't this how you ice glasses? Ben, you never realized what you can do with this liquid nitrogen you have, did you? The perfect way to ice glasses. Yeah, provided they don't break. I think that's the plastic that's breaking. Normally, when you do this, you only have to put ice for a little while, but this is very dry here, right? Because it's so cold. So you have to cool this down a lot. But this is a good way to cool things down. Perfectly iced glass. Perfectly iced glass. An olive? One or two? Two, oh, okay, two. With this kind of ice, you don't need to add ice. And a nice cold drink. And what better way to end a talk than that? Thanks very much.
So, after a talk like that, I'm sure that there must be some questions in the audience. Right? All you home cooks out there?
Don't ask, I'll just drink this drink.
I believe there are some microphones that will be circulating, so.
Okay, so Easter just passed, and one of the things I do every year at Easter is pickle hard-boiled eggs, which requires peeling a lot of hard-boiled eggs. And I'm wondering if there's any temperature or what variables should I be paying attention to so I can easily peel those hard-boiled eggs every single time I
think
do
it
them.
should be patience. I don't really know. We had real problems peeling the eggs today also. I don't have any answers to that, sorry.
That is an occupational hazard of teaching a class like this. Everybody has questions.
Here, I've got a...
I remember when I was a kid, it was a rainy day, and I thought I would make divinity. And with divinity, you have to take egg whites and beat them. And you cannot beat egg whites on a rainy day. And I can't remember. It must be something with the pressure. I don't know. Do you know why egg whites wouldn't beat?
You know, I've never tried to beat egg whites on a rainy day. I've always done it on a... So I don't know. I honestly have no idea why. Because egg whites really should beat very well.
But my mom laughed at me because she knew that there was no way egg whites would
Did you
whip
use a
up.
copper bowl?
Pardon?
Did you use a copper bowl?
Copper bowl?
Copper.
Copper, no.
Apparently copper bowls work better. Another sort of, expert's tale, which I don't know the answers. I have no idea why that's the case. I can't imagine why. So I'm sure there is.
I think it has to do with the atmospheric pressure. The moisture in there, I mean, that's what, unless that's an old wives' tale, because even on certain times when,
you're trying to make meringue. Again, you're adding the air to the egg whites.
So that
and
means that in Denver, you'd never be able to make egg whites.
Well, it has to do with moisture too.
I see.
Humidity. Well, same thing, the moisture in the atmosphere.
Sorry, I don't know.
We have a question over here.
So I have a question about the alginate that you're using. I noticed that you use like a huge scoop, I guess. So I presume if you, I may be wrong, but if you used a small sample, you'd have perfect spheres, I guess?
Can you speak into the microphone? Sorry.
Oh.
I can't hear you.
You used the gel, right? Or raspberry?
Yes.
And you used a huge lump sum to sort of form a thin shell around a thin thing. So if you probably used a smaller sample, you'd have something that's kind of perfectly spherical, or not?
It's a matter of practice of how you put it into the alginate to make it perfectly spherical.
Oh, all right. So then.
So Elena didn't have the opportunity to practice with this particular yogurt. Otherwise, I'm sure she would make perfect spheres.
All right. Because I was going to, is there, your sphere sort of seems to, for lack of a better word, erode over time. Is there a way you could have that sort of shell stable for a longer period? And imagine you could.
Well, if you want to stabilize it, if you're doing the reverse spherification, so you're building the gel on the outside, you just the more stable it is, the longer you let it stay in the alginate, because you get a thicker and thicker shell. If you're doing the direct spherification, then you just wait longer time. So Elena is taking out some caviar, I call them, some small drops, but I'll bet they're completely gel. You want to just try one and see? A spoon? It's more or less completely gelled.
Thank you.
Do we have other questions?
Do you have a website where we can, or YouTube videos where we can learn more about the physics of cooking?
Okay, so what's on the web right now is the public lecture. So we do a public lecture with the chefs. But we're going to put the whole class online this fall. So everybody in the world can take the class with us. It's going to be completely free. It's open to everybody. It's through edX, the Harvard-MIT collaboration for putting classes online. So we're doing it online, an online version. So starting around October, I think we're going to launch in October, you can take the whole class. It's going to be a class. All the lectures will be online. We'll have labs. We're trying to design labs that you can do at home. You'll be graded. So that's the best way for actually taking the class, if you're interested. Absolutely. Just imagine everybody clapping, the whole world clapping.
Isn't there going to be a physics of cooking class here at Augsburg as well?
Next spring, it will be offered again. Yes.
Okay. Just.
Okay. This is regarding the egg temperatures at which you cook them at. How does foodborne pathogens factor into the temperature? Are they killed off by those temperatures?
It depends. I mean, as with all foods, it depends on the temperature. Sometimes the temperature that you have to cook a food to kill the pathogens is higher than the temperature that you want to cook food. That's why if you go to restaurants or places like that, they always tell you eating raw food is dangerous to your health because you're not killing all the pathogens. So you want to be careful when you cook. It's, the way the chefs call this is called sous vide. It's cooking at a fixed temperature. You have to be very careful about keeping your food clean and keeping it safe. But there's a lot of studies that have been done, and I think now it's pretty well understood how to do it in a very safe way. But you do have to be careful.
Any other questions? Up front.
Spherification or reverse spherification?
Well, you can buy kits. You go to Modernist Pantry, I think it's called, online. You can buy kits to do it. So yeah, it's.
Anything we buy or in a restaurant?
You go to many restaurants will serve it now. Many modern restaurants serve it. But I don't know. I think you can buy caviar that's made this way. I think Ferran is selling that.
My students keep telling me about some sort of bubble tea yogurt place somewhere in the dinky town, right, that has spherified little gel juice droplets that you put on your frozen yogurt or something. The name is escaping me, but they keep telling me about it, so. I'm sure
Actually, I can speak to that. There's an MIT kitchen chemistry course that does a section on molecular gastronomy. And if you go to willpowder.com, they have kits for spherification, reverse spherification, and it contains all the materials that you need. And then the kitchen chemistry course has some recipes for cola caviar and mango gnocchi. So that would be a good place to find it, is willpowder.com and then the MIT kitchen chemistry.
That's that school down the road from us. There's no cooks there. Go to edX, EDX, or just look that up. And if you find the website, I'm pretty sure it's just the website's edX. If you just Google edX, you should find it. If you don't, send me an email, I'll send you, I'll find out where it is. But I think right now they've already listed the course. So, I'm sorry? I can't.
MOOC, right, massively online.
Oh.
Course. Or
Yes. Thank you. Me, I know it's just a lot of work. I mean, we're filming it now, so we're putting it all online.
Good question. I recently watched a video of Chef Cooking making eggs with particularly a child, and they made runny eggs, which maybe many less parents don't care for so much. And I'm just wondering if through teaching the course, if it changed your sort of taste or perspective on food.
It certainly changed my perspective on food. You think I could ever do anything close to this before I taught the course? Are you kidding? So yeah, I mean, I learned a lot, but I learned a lot about food. I learned a lot about the science of food, which is sort of fun. I certainly appreciate what the chefs do and enjoy them enormously. They're exceptionally creative people. And I guess I appreciated something I didn't before, and that is the interest that people have in cooking and the way now, the pedagogy that you can use to cook, to teach science, which is what I really do.
Cool. Well, let's thank our speaker once again.
And if you want to taste anything, Elena might do some spherification for you if you ask her nicely. Please go ahead.